So, hi folks, this is me, Vishwas Narayan. I'm the creator of this podcast, and I'm also a researcher who's working in deep learning. So, this is my podcast. Do check me out on YouTube and have a lot of podcasts done and a lot of other things. So, if you want to know something more about me, it's better to just hop in on LinkedIn, just give me a ping. I'll be there ready for you folks. So this session is going to be on something which is more of an introduction to your AI and deep learning. And that's what we are always thinking about. But I was always thinking about like, how can we really give ourselves a chance in order to give somebody a new way of learning? And I was like, all right, so let me just do one thing. Let me just do a new section on sensor fusion, because sensor fusion is something which is more cool. And today, when you think of something as good as deep learning, sensor fusion plays a humongous role. And let me just give you a quick intro about what this tech is all about. So you have a cloud instance which is as good as this. There is a set of compute, which is CPU, RAM, and there is GPU, which is doing all the mega processing, and AI is always communicating about the requirements that has taken place into the consideration. So there are hundreds of processors which run, and not just this, you can consider this as 100, you can consider it as into thousands, and there's a way more beyond complexity. That's where the cloud computing gives you a lot of instance where, of course, there's an AI system that can really make a lot of changes. And that's where it requires a lot of compute. That means that you are able to train faster and iterate faster and things like that. But let me just say you have design and complete different entity. Like you have some sort of an analysis done through something like a self-driving car. So a self-driving car is something, an autonomous system where you're thinking of like, hey, what can it do for the future world? And now you are embedding it with a lot of data from different sensors, and different sensors come and starts communicating. So sensors have their own way of working. So sensors will always be attached to it, and there'll be hundreds of data which comes in and goes out. So it's a two-way communication that happens, and there is a lot of actuation command that goes in, and there is a lot of commands that always cater on the precision of all these kinds of documents that we are writing today. And when you think of something as good as an AI, this is what you're talking about, and this is what you're basically believing in, and just getting how the things are being worked out. And basically, this is what your entire system is all about. And now, what you see is you have all these right now, and you have all the analysis done. You have all sort of data which is being collected, but there'll be a point of time where one sensor, let me just say sensor one, is connected with respect to sensor 2, and now you feel that, all right, let the both start communicating. That means the way in which they're communicating is a data, and this is also a data. And there is a lot of buses like which are already there: LIN bus, CAN bus, local area interconnect network, control area network. This is what we call the LIN and the CAN. They are really a high speed way of communication. That is like, it's not I2C, which is actually from Philips, which is making a huge change. But here we are talking about something as good as an AI system that makes a good amount of changes to you. And basically, when you think of something as good as this, you really want some sort of an intuitive analysis to be done. And this is where your sensors come into the picture and they start working. And so now you have got some sort of an AI system which says to you that, okay, that you have hundreds of hundreds of sensors which are communicating through LIN and the CAN buses which are there here. But what if this goes through a fault? And the basic aim of your entire system is how can you make it more fault tolerant, and how can you make it more fault proof? And this also comes out with some sort of a security aspect, where security of the application is also being considered. And there is always an AI system that says, hey, this is what I'm capable of doing. If you want something, write an algorithm for that. And this is where sensor fusion comes into the picture. Of course, we have LIN and the CAN. Let's say there is a LIN bus, there's a CAN bus. Sorry for that. It has to be all caps. So it's LIN and CAN, which is communicating here, where it's communicating through a CPU. A CPU is always a fundamental unit of any compute that you're looking at. Like, it's like, okay, now you have set of buses, now you have set of compute inside, and how you are communicating through that. And LIN and the CAN buses come here and they start communicating. And let me just say, there is a quick thorough note of the sensor, which is nth number, and this stops working. And this becomes a huge impact on your entire analysis that you are going to do tomorrow. And basically, when I think of all these kind of systems, I always think of like, what if something goes wrong and what if I can't get it right? This is where entire architecture is designed for. And also, if you think of something like this, there is always a chance that your CPU might not be good, and you have an extra accelerator for edge, which is edge GPU, which is always there, or is an edge FPGA. FPGA is a field programmable gated array, a field programmable gated array, grammable gated array is something which is cool enough in order to give a sort of a configurability for your hardware. Let me just say this is a set of hardware which now has the capability to just behave as a CPU. But now, what if I have an hardware which can bisect and start communicating as one unit here, another unit there. So it's a unit 1 and it's unit 2 here. So everything has its own way of working. So that's what's the edge with your field programmable gated array. Field programmable gated arrays basically starts the construction of every single little sort of and configurable aspects into one place, and everything starts working perfectly. And over the course of time, when you think of something like this, the GPU, which is doing tensor operation, and there's a CPU, which is doing a sort of a digital translation, there is a chance that this can adhere noise and even this. So there is always that chance that all of these can give out noises. So a strategy in order to give more sustainable and more well architected framework for sensor communication is what sensor fusions are all about. So let me just give a quick note on what this sensor things is all about. So yes, so let me just grab this, let me just grab this, and also yes, perfect. So let me just start with the data generation of the test data set. What I'm doing is I'm just importing NumPy, Matplotlib, and TensorFlow in order to just get 100 observations. This is where I'm generating my own set of data sets. I'm just giving a neural network and analysis. And I'll share these notebooks to you guys. Don't worry about that. Everything will be in your hand. And what we are just trying to architect here is we have 100 numpy arrays and thousands of numpy arrays. Can I just do it on a vanilla Python? And it's impossible to do on a vanilla Python because it's memory intensive. So numpy is memory optimized for all these kinds of operation of arrays. And what you are doing is you have 1,000 operations, you have excess, there's X samples of, let me just say, which is just taking out and this dimension and ZSS and Z dimension, and there is generated inputs, which is XS, and there is always a noise which is added because we love to see how are these noises being affected in the sensors and everything. And there is a generated target which is always there. So a generated target can be as good as you designing a black box. Of course, every system today is a black box. If anybody is in a distributed system and compute classes, and they will get to know there is a set of input and there's a set of output which is a function of input. So this is the F which starts making sure that everything starts working proper, and this is what we call as the function. And even if you generally look at some sort of a neural network, there is always this structure which is X, F of X comma W, and this is summation of it. This is what we always talk towards, and this is also a similar thing. A neural network is also a black box, and your function, the input and the output CDs, is also a black box. Let me just say there is a capacitor which is there, and of course I know this is too much of ECE, but this is forward. So there is an amount of positive and negative charges, and everything can't be that precise on a machine, and everything has its own trade-offs. So that's where we are adding noises here. So noises are being added here. So there is an always. So what we are doing is np.save z, which is doing an tf.intro, and everything is being saved. And npz array is being taken, and the training data is considered. npy.io is saying that it's a numpy array input and output file system, which is having a numpy array in it embedded. So an array of tpz and a data type of undefined data set of 12 bits, and also there is a lot of definition for it. You guys can check out what is this u12 in numpy. u12 in numpy is in a pandas, and if you can think of all these, it don't see the difference. It's like an object store which is always there, and it's always communicating with everything. And this is what we are doing. We are just making sure that the kernel works proper. And this is just a simple neural network that we are doing with a sequential. And this is a one layer neural network. So we are just giving 100 epochs because it's a very small data set. And also the collab has good amount of compute here. So model and the layer have their weights and everything. So there is always a weighted layer, which is always communicating here. And there's always a bias, which is always working. And there is always a model prediction that always starts working about how can we really get to know. So this is a simple example of you have hundreds of data from different sources, and how do you compute it? And this is where the predict model comes into the picture. Of course, when you see something as fit here, this is where you're training the model, and you're trying to just analyze all the features back from your input and output model that you're generating. And now what you have right now in your hand is a prediction model that you're just thinking about, hey, there is a set of inputs, there is a set of outputs. Now we have also have the test data set. How can we utilize it? And this comes in handy for you. And if you think of, sorry for that, I think a lot of other connections, so that's fair. So it's very simple. What I've done is I've just bought in the necessary libraries, And what I've done is there is an generated train data set. So sorry for not giving the data set. This is one of my final year project, and my guide didn't give me the data set, but yet, I'll be sharing it in the future. So don't worry about that. It will be there in the comment section of that video as well. So there is always that one way in which you read, that's always pandas, and you start describing it, and you have a lot of other tail, head, everything has been defined here. And value of the count is, it's a D type of int64. That means it's a 64-bit integer type data set. That's what we are computing towards. And applying and undersampling is where we are just making sure that all the classes come in our hand. And there's n number of samples of 800. And 800 samples starts working. And the data of 187.value.counts has been added. In a similar fashion, what we do is we just do the train test split, and this starts working. And every time, oh, sorry for my typo. It's a neural network architecture. Texture and everything starts working. What we have done is we have just taken the convolution neural network and we have brought in the neural network. So where is the neural network taken is from the TensorFlow here. So sklearn, as you know, it's used for data wrangling and data analysis for the prerequisites, and everything starts working. So there is convolution of one dimension, which is having a kernel and activation function. So padding will always still remain the same, and we are just doing the padding operation here. Neural network added a dense layer of compute. Dense layer is basically the depth, which is defined here. So depth is something like you have one set of neural network here and the other set of neural network here, and it goes on. And it's something like just move through the complete depth and iterate backwards. And this is what we are trying to accomplish here. And this is where the dense layer comes into the picture. And of course, there is always a compiled version of all these models. And you have an Adam optimizer, adaptive momentum. Adaptive momentum is a very great example for all your sensor fusion application. I'll say you how. If we all expect the loss functions to be like this for all the training and the epochs, but we want a minimum loss here, but the greater amount of epochs. And it has to be something like it has to always iterate back and forth here and then reach the maximum, because we want that to learn good amount of matrices. And the more they learn good amount of matrices, more is the reason for us to just take a new neural network architecture and consider it, why can't we do something else? And this is where we are training every new model towards, and we are just starting to work with all the things like AI is something new, deep learning is something new, and there is always a way in which you can make, and also there is always a system that can really go wrong. And that is where we are just trying to architect something towards an AI system which can really make some good decisions. Some good decisions really make sure that we have architected something which is great enough to just really get to know how are we working towards an AI and an hardware industry. That is where your entire neural network architecture comes into the picture. And when you think of all these, we have a generated test data set. So generated data set is what we'll be having. And basically this is not generated, but we just collected it out from the different sources of hand grip strengths. So we have it and we do the data processing. And what we have at the end of the day is we have trained it, we have tested it, and we are now predicting all these values with respect to this. And we finally achieved an accuracy of 96%, which is pretty phenomenal for an application like this. Because when you think of some sort of an application like this, which we have mapped here, just get to know that we are using a Tesla T4 architecture. We have used a command called as NVIDIA SMI. And there is always a reproducibility of seeds, which is always thinking about. These are all generated data sets that we are mapping it towards, and we are just generating out the data sets. What we are just trying to do is we are just trying to just ratio of zero point 0.7 is the training data, testing data is 30%, so it will be 0.3. And we are now separating out all the rows and the columns which can really give us that data set. And what we have now is something called as a class scalar, and we are getting the scalar operation, and we have a different set of data sets which are already there. So if you think of all these are some of the trainable parameters. So this is just a simulation of what sensor fusion data looks like. Sensor fusion data looks like this, and they start communicating with all different sensors. And there is always a neural network that we are just doing. So this is a one layer neural network that we just built for a reason, because every neural networks does the compute. And what we did was we have I predicted on hyperparameters of 47, actual number of hyperparameters is 47, and number of data is 10,000. And what we have in the next column is very, very rude, because now we are getting a loss of 0.345%, which is almost equivalent to 75.5% of accuracy. It's not 75.5, it's 65.5% accuracy, which is pretty nominal for any sort of a neural network architecture that we are building. And first of all, it's a one layer architecture, and secondly, this is working on a trainable data sets. So after we get the losses, I just get to know, okay, the test losses are around the 31.94%, which is pretty much equivalent to 68% accuracy in the test. And we have all the predicted values here. So right now, what I just showed you guys is very simple architecture, which really talks about how are we architecting towards a sensor fusion data set. This is just a simple example. If you want anything more, do reach out to me personally. I can help you with any sort of a sensor fusion data set, where we are now trying to architect something which is as good as a neural network which can make decisions in the real time, and also a neural network which can make decisions for a fused amount of data sets. And what I just showed you is just a simulation of it. But if we go to some extreme levels of data set, you can think of application like lidar. Lidar is pretty good application, and it starts working in a pretty good fashion. So do check it out, folks, and thank you so much. Do enjoy this entire arena, which is being organized by TFUG and GDG Mysore. And thank you so much, Usha ma'am, for giving this chance for me. It means a lot. And it gave me a chance to relearn some new stuff. And this is what we do when we are researching something using sensor data and sensor fusion. So thank you so much, folks.